Okay, the next objective in this section is to apply the fundamental theorem of algebra. Couple of things before we talk about it. The set of complex numbers includes the set of real numbers. And if you'll remember last time we talked about a complex number is of the form a plus bi. If your b is 0, so this part's gone, all you have is a real number. In your complex number, if a is 0, you have what's called a pure imaginary number. And if a and b are both non-zero, you have what's called the complex numbers. So the complex numbers contains the real numbers. So you're being asked to find the zeros of a polynomial over the complex number system. So like I just said earlier, you're wanting to find the real zeros, we call them the red ones, that you can actually plot on a graph, their x-intercepts, and the purple zeros, the imaginary ones. So you're finding, over the complex numbers, you're finding the real zeros and the complex zeros. Only the real ones correspond to your x-intercepts. The complex ones are just purple zeros that just float around. They're not on your graph. All right, two theorems. Linear factorization. Every polynomial can be factored as a product of linear factors. So if it's a degree n, you can have n linear factors. That is a huge and powerful theorem. It takes a long time to explain why. Just know that you can write a polynomial as a product of linear factors and move on. You can write a polynomial as a product of linear factors. Know that those linear factors might not necessarily be unique because you have multiplicities greater than 1. All right, the second big one here, number of zeros. If you have a polynomial of degree n bigger than or equal to 1, how many complex zeros do you have? Exactly n zeros. And that's why all day today I've said if it's a degree 4 polynomial, how many zeros do you have total? 4. If it's a degree 6 polynomial, how many zeros do you have total? 6. They may or may not all be real, but you're going to have 6 zeros if you have a degree 6 polynomial because of that theorem right there. You also have the conjugate zeros theorem that says if you have a polynomial and you know a plus bi is a complex zero, then you also have its conjugate a minus bi. They come in what are called complex conjugate pairs. That's actually worth writing. Complex conjugate pairs. A plus bi and a minus bi. The next example says, given this polynomial, and you know that 1 plus 5i is a 0, can you immediately give me another 0? They have to come in complex conjugate pairs. If 1 plus 5i is a 0, then you know that 1 minus 5i is a 0. So how many zeros do you know right now? 2. How many are there going to be total? 4. You know 2 of them. Go do your synthetic division and reduce it down to a quadratic. All right, so I know that 1 plus 5i and 1 minus 5i are zeros. I'm going to go put those in the half box. So 1 plus 5i. And what are the coefficients going to be? 1, negative 2, 28, negative 4, and 52. Do you agree? Those are the coefficients from the polynomial. So now I'm going to do the synthetic division. Bring down the 1. 1 times 5i is 1 plus 5i. When I add negative 2 plus 1 plus 5i, I get negative 1 plus 5i. Then I'm going to jump over to my calculator because I don't like multiplying complex numbers by hand. I need to do 1 plus 5i times negative 1 plus 5i. So 1 plus 5i times negative 1 plus 5i is negative 26. That goes here. 28 plus negative 26 is 2. Now I need to do 2 times 1 plus 5i. 2 times 1 plus 5i is 2 plus 10i. Negative 4 plus 2 plus 10i is negative 2 plus 10i. And now I need to do negative 2 plus 10i times 1 plus 5i. So 1 plus 5i times 2 plus 10i. Was it 2 plus 10i? Negative 2. The I is second and the decimal point. And I got negative 52. And that's good because 52 plus negative 52 is 0. Okay, give me another number to put in a half box. 1 minus 5i. Exactly. So I want to go put 1 minus 5i here. Okay, bring down the 1. 1 times 1 minus 5i is 1 minus 5i. What do I get? 0. 0 times 1 minus 5i is 0. Bring down the 2. 2 times 1 minus 5i is 2 minus 10i. If you don't believe me, do it on your calculator. 2 minus 10i, and I get 0. Okay, I have 1 plus 5i as a 0. I have 1 minus 5i as a 0 because complex conjugate pairs, zeros come in complex conjugate pairs. What polynomial do I have left here at the bottom? 1x squared plus 0x plus 2. So at the bottom I have x squared plus 2 equals 0. I get that from these coefficients. X squared will equal negative 2. X equals plus or minus the square root of negative 2. So x equals plus or minus root 2i. This was a degree 4 polynomial. How many zeros have I found? 4. What are they? So for part A, the zeros are x equals 1 plus 5i, 1 minus 5i, root 2i, and negative root 2i. All four of the zeros are complex. If I were to graph this polynomial, how many x-intercepts would I have? None. Yay! Okay, part B says to factor it as a product of linear factors. What are the four factors? They're going to be x minus 1 plus 5i. What else? X minus 1 minus 5i. X minus root 2i. And x minus negative root 2i. I just wrote the polynomial as a product of linear factors. Okay, next problem says to find a third degree polynomial with integer coefficients, and it has zeros 2 plus I and 4/3. How many zeros did they give you? Did they really only give you 2? They really gave you 3. What's the other one? Uh-huh. So they gave you 1, 2, 3 zeros. What degree polynomial do you want? A third degree polynomial. So did they give you all the zeros? Yep. So now go write your polynomial. So they gave you the zeros. Go from the zeros to the factors. So here we go. F of x equals x minus 2 plus I What's the next factor? X minus 2 minus I. And then that other one, you can do x minus 4/3, but I told you I don't like doing it that way. I told you to set x equal to 4/3 and then multiply both sides by 3 and say 3x minus 4 equals 0. Again, instead of saying 3x minus 4, you can say x minus 4/3 if you want to. But I like doing 3x minus 4 because it keeps the fractions away. Okay, that is a third degree polynomial with those 3 zeros. But what else does it say in the directions? It says with integer coefficients. So that means they want you to multiply all that junk out. All right, it's not hard, it's just a matter of distributing. I'm going to distribute that negative and that negative. So here comes x minus 2 minus I times x minus 2 plus I. Okay, here goes the game. I need to distribute this x to all 3 of those. What do I get? I get x squared minus 2x plus xi. Now I need to distribute this negative 2 to all 3. And I get negative 2x plus 4 minus 2i. Then I need to, I'm going to erase the green, then I need to distribute the negative I to all 3 I'm foiling but with 3 terms in each. Negative I times x is negative xi. Negative I times negative 2 is plus 2i. Okay, here comes negative I times positive I is a negative I squared, which is a negative 1, which is 1. Instead of doing negative I squared, it's a positive 1. What else do I have to multiply all that by? 3x minus 4. Exactly. So I still have times 3x minus 4. Let me pause it and let you catch up. All right, now let's see what kind of goes away. Do you see the xi's are going to be gone? Xi minus xi. Minus 2i plus 2i. What's left? I have an x squared, and then I have a minus 2x and a minus 2x. So I have x squared minus 4x plus 5. I have a plus 4 and a plus 1, so plus 5. Times 3x minus 4. We're going to distribute it again. So the 3x, I'm going to do that times all 3 things. I get 3x cubed minus 12x squared plus 15x. Then I'm going to go take that negative 4 and hit it with all 3. And I get minus 4x squared plus 16x minus 20. What's my answer? 3x cubed minus 16x squared plus 31x, good, minus 20. What did we just find? We found a 3rd degree polynomial with integer coefficients that had the zeros 2 plus I, 4/3, and 2 minus I. So up until now, I've given you the polynomial and asked you to find the zeros. Now I gave you the zeros and asked you to find the polynomial. Last example, find a polynomial f of x of lowest degree with zeros -3, which has multiplicity 2, and 5, which has multiplicity 2, that satisfies the condition g of 0, that should say f of 0, by the way. F of 0 equals 450. Okay, you have 2 zeros, correct? You have the 0 -3 and the 0 5. So I know that my polynomial has to be x minus -3 and x minus 5. You agree? Those 2 factors have to be there. Now I've got to deal with the multiplicity. If it's multiplicity 2, what does that mean out here? They both have to be squared. So let's go multiply all that out and see what you get. Okay, I'm going to go do x plus 3 times x plus 3 and x minus 5 times x minus 5. I will get x squared plus 6x plus 9 times x squared minus 10x plus 25. Now you're going to have to go do that FOIL thing again. I'm going to multiply the x squared by all three things. And I get x to the 4th minus 10x cubed plus 25x squared. Now I'm going to multiply the 6x by all three things. And I get 6x cubed minus 60x squared plus, what is that, 150 x? Is that right? Okay, last, I need to go multiply the 9 times all three. And I get 9x squared minus 90x plus, what is that, 225? Okay, collecting like terms, I have x to the 4th minus 4x cubed (25 minus 60 plus 9). 25 minus 60 plus 9. I get negative 26. And then 150 minus 90. 260? No. 150 minus 90 is 60. And then plus 225, yes? All right. I also need it to satisfy the condition that f of 0 equals 450. If I were to plug 0 in for x right now, what would I get? If I plugged 0 in for x, I would get 225. I want 450. So this is how you do it. I say a times all of this. And now I want f of 0 to be 450. So 450 is supposed to equal a times 225. Because all that stuff underlined, what happens to it? If I plug 0 in for x, all that stuff that's underlined turns into 0. So a is going to equal what? What is 450 divided by 225? 2. So a equals 2. So what is your answer? What is your polynomial? If a is 2, so watch this. I go change this to a 2, and I need to distribute. What's my answer going to be? 2x to the 4th minus 8x cubed minus 52x squared plus 120x plus 450. That's my answer. That polynomial satisfies the condition f of 0 equals 450 it has two zeros, both with multiplicities 2, and the two zeros are -3 and 5.